The Contain project is our response to the COVID crisis. Our model was to try and create a high-throughput, automated COVID testing laboratory in a shipping container. When the COVID outbreak happened, we used our network to have a big open call for anyone who might be able to help us develop this Contain project. Anyone with expertise in the PCR test itself, automation, laboratories, shipping containers, anything really. We had a lot of people from across the UK in different institutions. We had a lot of people across the US as well. Some of the heads of companies who are working with the automation robots. Some people who have developed new open source reagents, people from public health services in England and Wales. And we also were in a lot of contact with people who were organising governmental responses in different countries. And quite quickly we had a team of over 200 volunteers. And this really enabled us to very quickly finish the project in a way that we wouldn't have been able to do with just the 5-person team. The automated process that we have means that in a single laboratory in a shipping container, we can get about 100 tests through every 45 minutes, running in parallel. So in a normal working day, this can be over 1,000 tests with a single operator.
I think it's kind of important to think about the fact that we use the term coronavirus testing kit, and really it's not about a kit. It's not like a pregnancy test or a water testing kit. You really need this large facility filled with very expensive equipment to do this test. The most common way to do a coronavirus test is interestingly, it's actually a very common technique that anyone who does work in a biotechnology lab probably does almost every day. It's called a polymerase chain reaction, or PCR. So when you think of a virus as essentially a piece of genetic information trapped in a little bubble that protects it. And all we're really doing in this test is opening that bubble, pulling out that genetic information and then running this test onto that piece of genetic information to try and test to see if it is the coronavirus or not, or SARS-CoV-2 technically. What people are often familiar with when they think of coronavirus tests is the actual process of swabbing someone. One of the issues that a lot of national governments were having is that the actual swabs, all of those components, were in such high demand that there wasn't good enough supply of them. So we tried to design this project to actually be very flexible, to work potentially with swabs, but also to work with other techniques. So another technique that's very sort of up and coming in terms of coronavirus tests is saliva. If anyone's done a 23andMe, it would be a similar process where you would essentially spit into a tube and then the test is done in that tube instead of somebody jabbing a swab to the back of your nose. And so we really wanted to make the product to be flexible with those other tests. The whole process is sort of separated into 3 separate steps. And so what happens in the first part of doing this test is you have to take that sample, inactivate it and sort of rip it apart. It's called lysis. You break apart the human cells, you break apart the viral particles, and you do that by adding chemicals to it. In station B, this is where essentially we're doing technical processes called RNA extraction. So the coronavirus, it has genetic information inside it. I think most people have heard of DNA. Well, the coronavirus actually has something called RNA instead of DNA. And in the RNA extraction process, we essentially isolate that RNA and we wash it several times. So this is where the actual robotics comes into play, because this process is quite labor intensive. Essentially, it involves binding that RNA using some sort of material. So in our specific case, we use something called a magnetic bead that's coated in something that will bind RNA, and then sticking that to a magnet and essentially washing it several times. You would add the sample, this sample that's been lysed, been broken apart, to magnetic beads. You would then wash it several times with ethanol, alcohol essentially. And then at the end of that, you'll have a clean sample of hopefully just human and/or viral RNA. And then the final step, station C, involves actually preparing the sample for PCR. So in this specific situation, for a coronavirus test, you do a certain type of PCR called reverse transcriptase quantitative PCR. Essentially what that does is take this viral RNA, convert it into DNA, and then essentially amplify it. Because at the end of this process you may actually have very little viral RNA left, a lot of it maybe gets lost or there wasn't a lot in the sample at the time, you also have to replicate it multiple times. So that's essentially what the final step of this process is. We prepare a reaction, again using an OpenTrons robot, where we mix the sample with enzymes, and those enzymes will then replicate it multiple times, and we'll have a probe to test whether there's viral RNA in that sample or not. This is the exact machine that the government uses. So the government essentially went around to all the universities in the country and asked for these machines from them. And they actually have a big room in Milton Keynes filled with these machines that they're doing all the testing on.
The sort of scenarios that we're considering for the Contain project and where it might be really effective is in sort of mid-sized to large institutions and companies who are looking to kind of get back to operation, get back to work. Maybe it's a university that wants to bring its students and staff back to work safely. And to do that, they need to have regular testing of their employees and their students and people. And one of our Contain units, if it's able to run about 1,000 tests a day during normal working hours, it can test a medium-sized institution of 30,000 people every month. The other advantage of the labs is because they're mobile, because they retain all of their shipping permits and everything. As the outbreak progresses and moves across the country or even across the continent, you can very quickly move the laboratories to a new location where perhaps there's an increased outbreak and start servicing that area within 24 hours for most of Europe. I think particularly for countries that were seeing this spread across the world, but their countries hadn't been hit in the same way yet, and particularly countries that didn't have or don't have an existing high-quality laboratory infrastructure. They're very interested in something that could provide them with that testing infrastructure very quickly and at a sort of affordable price, rather than having to, in China they can build a hospital in 7 days, and that's great, but that's not an option that's available for a lot of countries. So this is something that can be built somewhere like the UK and shipped across the world very quickly, when the speed of response is really, really crucial, I think. Yeah, so we don't know at this point if COVID is going to be something that's around for a few more months and then it sort of dissipates, or if it's going to be with us for years and years. We also don't know if there's going to be similar outbreaks going forward, but certainly with increased population density, we're only more and more vulnerable to outbreaks like this. So yeah, making this project open source and having it available for anyone in any country to replicate as quickly as they want to means that hopefully we'll be better prepared in future years for this crisis or similar crises.